Let's start. Thank you everyone for joining here today. Good morning. My name is Ishwan Khan, and I have my colleague here, Obed Mogaka. And today we are presenting the TinyML workshop, so building efficient AI for the edge. So about Obed, he's doing his PhD here in MD, and his research is focused on accelerating deep learning inference on FPGAs when you don't have a hardware work, and takes a quite of like focus to work on this. And I'm working on. I'm also doing my PhD, and my main focus is predictive learning and neural architecture side. So it's basically the intersection of these two fields. So today's workshop agenda we have. So this is the introduction to the seminar. I'll do this for 15 minutes, and after this introduction, we will be having the quantization section that will be presented by Obed. Here you will be studying four techniques for size and latency, quite interesting, and then we will have a 15 minutes coffee break. Some hands-on demo related to pruning as well as quantization, and also study about model pruning. So how do you so that would be go for 1 hour or 1.5 hours. Then we will have a nice break. After that, my session will be on knowledge distillation, how we can train smaller models by using bigger models. How models can go and work with the edge devices. So pretty interesting stuff. And after that, it will be a section dedicated to neural architecture such. How can we automatically design models using AI? So using AI to build AI. So that's a interesting topic. Then we will have a coffee break, and at the end, we will have a hardware deployment demonstration. It will be in class, and will be Obed would be trying that, and it would be quite interesting to see in real time how we deploy these models on an edge device. So let's talk about Edge AI. What is Edge AI? Basically, we have when we started with machine learning back in 2012, when deep learning had started. So it required lots of compute, and so it started an era of machine learning and deep learning, and so lots of people were experimenting on this using really high-end GPUs and resources. And so with time, it was necessary to transfer these big models towards embedded systems or edge devices that we have in our homes, like our mobile phones and other devices. So this created an intersection field called TinyML, or it's for short, it's called TinyML. And so, as I said, AI is everywhere these days. In our pockets, in our bags, in our closets, in our homes. So there is so much scattered compute around the world, and most of it is not used for AI purposes. So one of the main goals of this field is how we can enable using these devices that compute for AI, and how we can make lives better with these. So we have devices for medical purposes that can be apps on mobile phones. We have wearables, computer vision, and robotics, and other these IoT and smart cities. So what is the benefit of using AI, edge AI? What is the benefit of using these AI models on these smaller devices? The first one is diminished latency. You might have used these LLMs or different kinds of devices that when you are when you're using something on the cloud from your mobile phone, it takes some time to send some file or something, and then that is processed and take it back. So we want to diminish this time, and we want to remove this latency. So if our models are efficient and they are on device, then we can get a response instantaneously. The second benefit in this case is the bandwidth usage. Not always you will have a very good Wi-Fi connection. you might sometimes be relying on 4G, not always on 5G. So in such situations, you have to have such models and devices that can process these models well so that you can get results like LLMs. So if you are disconnected from these large language models from ChatGPT and Gemini, etc. So if one LLM is like that, your personal LLM is deployed on your computer, right? You can easily ask questions and make inference using that, and it would be like quite fast, as well as another benefit that we see would be private privacy would be also increased in that case. In another thing is that the real-time analytics and operations. So data processing and analyzing your data is directly on your device. So you have all the control of your data, and you can analyze that however you wish. But when you are using an online system, like an LLM that is hosted by someone else, you are sending all of your data there, and who knows what they are doing, how they are analyzing your data. So that is also an issue there. So that's not the benefit. The fourth thing is the data privacy that I mentioned earlier. By data privacy, we mean that, okay, whatever you are sending the information, maybe it would be a medical information that you are trying to diagnose something, or you are like sending some prompts that is most like popular these days. We are always prompting these LLMs. But one thing to consider is that we are sending sensitive data. So if these models, deep learning models are here in our local devices or our local systems, then we can be safe and quite confident with our data that it stays safe and it's not being used for wrong purposes. Improved scalability and reliability. So sometimes the clouds can fail as well. Like it's not faithful, and you might not have access to these things. As I mentioned before, for the communication purposes, the clouds that we have access to currently, they can also like turn off suppression. You might be in a critical situation that you need these devices. So I'm referring back to LLMs that take again because these are quite popular these days, and we are like using that on a daily basis. So if these devices are like on local systems, then we don't have to fear about that. We can just directly use them. So Edge has got the edge. I'd like to say like that. So it is faster, more efficient, secure, and reliable. So we need to move in this direction, and we are moving in this direction slowly and gradually because the world is full. And this is one of the main directions aside from distributed learning or predicted learning. Okay. So let's talk about the computational cost over the years that we have been having here. So initially, this was the first breakthrough. This was a convolutional neural network that started this image recognition and classification problem. And this was, you can see that the circle, the size of these circles denote models sizes, how big the models are, and then and this is the accuracies. The y-axis showing the accuracy. How high is this? So yeah. So you can say that how much has changed like over the years. So we have like efficient mobile net. So these are the edge devices that we have had over the years. And if we move towards the right, our computational capabilities have increased, while even with the smaller size, our computational capabilities have increased, and our accuracies on the ImageNet benchmark has also increased. So ImageNet is basically a benchmark for classifying images into their respective classes. So this is one of the most popular benchmarks that we have had over at the start of the deep learning era. Then we would like to talk about the third challenge, that is energy. So energy efficiency is like of the utmost importance right now, because as you can see that everyone's focus is on transformers, and transformers are the base for LLMs. And AI is responsible for 100 terawatt hours of electricity globally in 2025. Terawatt hours is a like really big unit for energy. And 100 terawatt hours, it's even like really difficult to even think the amount that it is. So with worst case forecast predicting a surge to 1,370 terawatt by 2035. So we need to work on this to make these deep learning models more efficient. So that we can have a sustainable future. Otherwise, it's not gonna go well for the Earth, the future of the Earth. So where is most of the energy consumed? So we have these different numerical representations that are associated with the energy cost. One of these is the object DRAM. So it is far more energy intensive than performing arithmetic operations. So you can say that if we are talking about operations, so these are like small scale. If you are looking at really small scale, so we have different types of operations. So integer addition would cost like 0.03 picojoule, and similarly, if we are talking about static RAM read of 1 MB, it would like 50 picojoule, right? So we have these on different graphs and how we proceed towards that. So this is like on a really small scale how we look at these things. So cloud AI hardware, let's talk about the cloud AI hardware. So cloud AI hardware, you can see that we have like big these GPUs, B100, B100, and over the years, this like they have like been developing like stronger and bigger GPUs that are capable of bigger in the sense that are capable of performing more compute. So if you are looking in these graphs, we have these teraflops. This is the teraflops, how many teraflops can be performed by different GPUs. And this is the memory bandwidth. This is the power that they consume. You can see that with time, power has been increased. They're costing a lot of power. And then the memory is also increased because, LLMs and these foundational models, they cost a lot of gigabytes of memory. Then we have the edge hardware, and one of the edge hardware is like the Qualcomm Hexagon DSP. This is generally used in tablets, mobile phones. The performance is not compared to actual GPUs, the big GPUs. So, but it is like really compared to them, it's like pretty power efficient. So it takes 10 watt, and the memory is also constrained to 16 GB. And the third thing here we are talking about is the Apple neural engine that is like used in iPads, iPhones, and its different devices. It is also sort of comparable to this Qualcomm Hexagon. And another device that is introduced is by NVIDIA. It's called the Jetson. And it's a family of like smaller devices, but it is like really capable of doing like the hard stuff that you want to do on an edge device. So by edge, what we mean like these small devices that you can use in everywhere, right? And then comes the microcontroller, the really small one, really the ones that like are powered by very small battery or cells that you have, and you want those to in places that you have like very low power access. So these are like utilizing them and like creating models and developing models that can be run on these devices is really necessary for tasks. It could be like an Arduino chip or Raspberry Pi, and even smaller that we have like ARM architectures and stuff. So we have to have devices that we have to have models and capabilities that can be run on these devices for different kinds of processes. For example, like the smart watches that we have, these are like really low power consuming for devices. So we have to have some models that can be utilized by these devices. So we have a summary here. So we have the cloud AI that uses the big GPUs that we have. Then we have the mobile AI. Then we have tiny AI that uses the controllers, these microcontrollers that we have. And these edge devices, the edge devices that we are talking about, this section, specifically this one, these have limited battery life. These have limited memory capacity and limited compute power. And all of these utilizes, the electricity that are provided by the batteries, right? So this is a sort of a model size comparison. So these are the x-axis is the release state, the y-axis is the model size, and shows the number of parameters. And you can see that the small models that is like with less number of parameters, less than 1 billion parameters. These are the circle ones. So initially we had this area, but now as we move towards this right top side of this graph, you can see that we have ultra large models with these diamond shaped symbol here. And they have like more than 100 billion parameters, and that amounts to a large storage on our hard disks as well as on GPUs when they are running on the server. So as we discussed, running LLMs on Edge is also very important for different purposes that we mentioned before. So deployment readiness matters for Edge generative AI. Let's see how this can be possible. So we have these IoT devices, Internet of Things devices, microcontrollers. We have the edge devices, phones or wearables. Then we have these edge servers and then data centers. And these are the devices how can be which kind of device that we have here. So if we are talking about less than 1 billion parameters, this one here, if you're relying on that, then this is challenging. And if we go towards the right, then our cases become ideal and more feasible. But this is you can say that this diagonal is the one that is challenging to deploy across these devices. So if we have 1 to 10 billion parameter model, then it's challenging to deploy on the edge or phone devices or wearable devices. But these are ideal for edge servers or data centers that we have. Similarly, for 10 to 100 billion, it could be ideal for cloud. It can be ideal for cloud, but not for servers that we have on small servers that we have schools or small setups that we have. So yeah, so you get a sense what we are dealing with here. So now by remembering these billions of parameters that we have, you have a good sense of what kind of devices that you can deploy it on. So if we give a summary of the overall workshop here. So we have these efficient deep learning models. So we have neural architecture search that searches for different blocks of the architecture and hyperparameters. And then it goes towards pruning and quantization. So this is basically our main area here, this pruning, quantization, and neural architecture search. And there are also some other things that can be focused on as well. This is code transformation that involves different techniques that we can compress this and make these models efficient. And also the model compression is also a technique that is also a part of pruning and quantization, and tensor factorization is another method of making these models efficient. So yeah, so these things, pruning, quantization, neural architecture search, and there is one more thing, the knowledge distillation I mentioned before. So there we'll also talk about that. So we went through the workshop agenda. So I will call our dear colleague Mo'obed to give us the session on quantization. Thank you, Beth.
So thank you. Okay, yes. So as you heard, my name is Obed. I focus on FPGA acceleration of deep learning. So in this section, I'm going to discuss about quantization. So just before I get into this, so we assume that at least you have an idea of the deep learning architecture. Basically, you have a model that has parameters, which we call weights, and then you supply some input into the model, that is in terms of maybe an image or a prompt, and then this computation that happens, and then you get an output. So having this general overview will be useful so that we understand now the fundamentals of quantization. So the overview of this presentation is about why do we need a quantization. Partly has been presented by my colleague, and then the fundamentals of quantization itself on what are the data formats for quantization, how to quantize, and then we see when to quantize, and then some aspects of extreme quantization. And then if we find some time, maybe introduce some advanced quantization topics. So then why do we need quantization? So the core problem is that by default, these neural networks or so machine learning is classified into various domains. We can have deep learning, we can have the traditional machine learning, and we can also have these generative models. This presentation is mostly focused on the deep learning concepts, but of course they can be extended to even large language models because they are now being quantized as well. So by default, neural networks are trained and run on this data format, which we call the 32-bit format. It's a very nice format that because it can represent large dynamic range of values precisely. However, this format is heavy in terms of like it has a large memory footprint. It also leads to very high memory bandwidth because you have to move a lot of data. And as we earlier saw that really the challenge with these models is that moving data is very costly in terms of energy. So we want to reduce how much data we move from memory to the processor. And then this is costing the power. So the solution here is to find cheaper number formats to make the model smaller, faster, and more efficient. And then this is the process we call quantization. So the challenges, as I repeat, is that we have the model size. So by using quantization, we can actually reduce to more than 4 times the parameters if we are using 8 bits. So 32 divided by 8 is 4. So we can actually go lower than this. And then we increase the speed. And then therefore we have more efficiency in terms of energy because the less the pages you have from memory, the less the energy you're spending in your hardware. So, however, of course, quantization comes with a trade-off because you will be losing some information when you do any quantization, as we will demonstrate. So formally, we can define quantization as the process of constraining an input from a continuous or otherwise a large set of values to some discrete set of values. So for example, if you are a photographer, you take, for example, a high quality image, it's usually very large. And then if you want to share it, that's when you process it and then deliver it in some JPEG or PNG format. You usually have to lose some information. And so that is the case in this case. So when we have this continuous signal, for example, if you're talking about DSP, you take samples of this data, then you will have some smaller values. So this is ideally the definition of quantization. So then to understand it more deeply, we will talk about some concepts about quantization and the number formats. So there are 2 ideas here. There's one, precision and range, how they affect efficiency. So as we said, the floating point number 32 is really a very precise number because it can represent a large range of numbers with great detail. Of course, it's low. And then when we have this other quantization formats like the integer 8. So we are using an integer which can represent a number between 0 to 255, or if you're using a signed number from negative 127 to 128 positive. So the quantized formats are extremely fast. They require less memory and power. They can, however, we lose some details. So our goal is therefore to find the sweet spot between this range and precision. So that is really what we try to do in quantization. So then some number concepts that we have to understand is the dynamic range, which is the span of numbers a format can represent from the smallest to the largest. So a number format with high dynamic range can represent, for example, both 0.0001 all the way to 100,000. And a format with low dynamic range then suffers on either of the extremes. So you could either be able to represent numbers that are huge, but not small, or the other way. So in a CNN, for example, in a convolutional neural network, this dynamic range is very crucial because some weight values are very close to 0, and maybe somewhere in the architecture, we have large values. So then means sometimes we may need a high dynamic range. Therefore, if we choose a number system that is of low dynamic range, then we will be losing accuracy. And then the other concept is of precision. So this is the level of detail we have in the number system. So that is the gap between two possible representable numbers. So high precision means there are smaller gaps. Those are the small steps that we move from for us to move to the next representable number. So for example, if we have 0.5001 and then 0.5002, sometimes they can be very important in a convolutional neural network. So if we have a number system that actually maybe doesn't have this as part of the set of numbers we can represent, then we are losing these two representations of the network. And therefore, this affects the accuracy. So these two concepts are important when we are selecting the number format to use. So again, I think this is also part of how to understand the number representations. So there are actually several number computing systems, but I just highlighted this as an example. We have an unsigned integer. So in this case, we can only represent positive numbers. And the n means how many bits in hardware we use to represent this number. So for an n bit, then we have 0 to 2n minus 1. So in this case, if we are using 8 bits, which is like the integer 8, then we can represent numbers from 0 to 255. So when we have signed numbers, of course, in convolutional neural networks, we have negative numbers as well. So positive and negative. So there are two ways of representing signed numbers in computing systems. It can be either a sign magnitude, so where we have a dedicated bit to represent the sign, so that the rest of the bits are used to represent the number itself. So this is one way. But there's also another one that is more common in computing systems, is the two complements representation. In this case, the challenge we have with the sign number is that we have two ways of representing 0, and that is wasteful and sometimes can be difficult to understand in hardware. So the two complements representation is more common, and it has a way of representing all the numbers. So when it comes to deep learning, therefore, of course, the floating 32, as I said, is the first one, the more that was used to train, and is mostly used to train the neural networks. It has 32 bits, so we are able to have a very high dynamic range and very high precision. However, the various companies, for example, NVIDIA, Google, try to figure out more optimal formats for representing the neural networks. So they came up with like the TensorFloat 32, where they actually it should be not 32. They call it 32, but they use 19 bits to represent the bits, the numbers. So it has still high dynamic range with high precision, and then this float 16 that has now 16, because they noticed that neural networks are far more sensitive to the size of the exponent. This is the value that controls precision, while the mantissa bits control the dynamic range. So they could just be able, they figured out that really we do not need all the 32 bits to represent these values. So again, we have integer 16, and so we are actually, you can say we are losing the dynamic range as well as the precision until even we get to integer 8, which has only 7 bits of the mantissa. And then meaning this, we do not have an exponent, we have very low precision. Basically, are moving in steps of 1. And that means we have no precision, even very low precision. So that's why we have another format that is more used in low-end devices, in microcontrollers, which is the fixed point number format. So where we introduce kind of an exponent into this mantissa bits, so we can have a fraction. So we can have this formula where we multiply a number of 2 raised to a power of the fractional length. So meaning we are introducing something like a scale to be able to represent more precise numbers. So this is quite a very efficient way of using the lower bits, but again, achieving good precision. So now we move to the quantization itself. So how do we quantize is our first question. So there are 2 or 3 main categories of techniques on how to quantize. One is the linear quantization or uniform. The other is non-linear, and then we will talk about some other called codebook quantization. So even in these, there are different subcategories. So let's start with linear quantization, which actually is like the formal way of quantizing. So this is basically an affine mapping of integers to real numbers. So basically we are doing some kind of transformation. So we have real numbers are the floating point numbers, and then you map them to a discrete set of integers in an affine or a linear way. So in this case, we would then have to define 2 parameters, and this is the step size and of course the scale, as I will explain. So this is simply to illustrate the quantization process in terms of bits, but again, more details in the next section. So here we have 2 domains. We have a floating point or the real domain, and then we have the quantization or the discrete domain. So because we are limited in number, the possible number of discrete values we can use based on the bit width. So if we have 8 or n, like any number of bit width, we will be constrained in the maximum and the minimum we can represent if we are using a signed representation. And so meaning we will have to clip or cut off some real numbers. And then using a step size or a scaling factor, we then represent these values using a set of discrete values. So then, so we can formulate these mathematically using these equations. So if we need to find the real number, then we have a scaling, which is a floating point number. And then we have the difference between, in this case, we take the Q either of the sides, subtract the Z. The Z is actually the 0 point. It's a way of representing the 0 point of the real number, which actually we can have it being 0 or some other number based on how we want to align our quantization. So this Z can be either 0 or any other number, but we will talk about it. So if you do this math, basically we can define the scaling factor as the dynamic range, this R maximum minus R minimum divided by the possible number we can represent in the discrete set. So this important to note. So for a quick example, so if we have a weight matrix, so we have a weight matrix with that 2-bit floating point, and then we have to quantize it to 2 bits of values. So in 2 bits, we can only represent 1, 0, -1, and -2. So this is our dynamic range. And we can set a 0 point. In this case, it's been chosen to be -1, okay, or it's learned we will talk about how to find the appropriate Z point. And then we have a scalar or a scaling point, a scaling factor. So if you try to remap it back to the floating point, you will notice that the values we get are not the same as the original. So this is now the effect of quantization. So meaning we are losing some details. And as you can see, we have now a quantization error matrix to show how much we have lost. So basically the objective of quantization will be to try to minimize the quantization error so that we try to preserve the accuracy as much as possible. So we talked about this the 0 point. Of course, there are two main parameters in quantization. This is the scaling point and the 0 point. So this is trying to relate these parameters with the Z because it will be one of the things we find in when we try to find the best quantization parameters. So basically, Z can be is actually found by rounding because we cannot find the exact values. We have to round up or down based on these parameters. So Q minimum will be having using this side of the domain. You subtract R minimum or maximum divided by the scale. So we find so to make it more sensible is to consider a matrix multiplication, which is the common operation in a convolutional neural networks. So we have a weight matrix and an input matrix, which will give us an activation or the output. So if we plug in a formula for finding the scale given the quantized output and the Z point of the output, so we can factor out and then find that really in this operation, we can factor together the scalars so that they are like one factor. And then you notice that find the quantized output, we just simply multiply the quantized inputs with the weights, subtract the 0 point of the weights multiplied by the quantized input. And then as you can see, the Z of the weights and the inputs are also multiplied together. And then you add the Z of the output. So you can notice that because we already in the beginning, we know the weight of a neural network. So we know the Z of the weights as well as of the inputs. But the output usually changes for every input you give to the model. So we will actually be finding the Z point of the output. And then since we know the weights, we can actually set it. What if we set it to 0? Then this will actually make this formula very simple. We will then have some of this set to 0. And that is why we will have what we call the symmetric linear quantization. So the symmetric means we just set this Z to 0 so that it perfectly aligns to the 0 of the real domain. And this actually simplifies the math in quantization. So otherwise, apart from the symmetric linear, if we had the Z being any other number apart from 0, then we will call this asymmetric quantization. And we will see its impact. But normally, this one is much easier to deal with in hardware than asymmetric. So again, to do it again, we now have the weights Z being 0. We have this formula. So to get the output, we have the scalars of the weights and the input divided by the scale of the output, which we will find during quantization. And so this is what we already know these values from the beginning. And we know the Z of the input and the quantized. So already we know this. So our objective will be to find the S of the output as well as the Z of the output. So mostly we ignored, okay, the example we had was basically on a simple matrix multiplication. But in neural networks, we have both weights, inputs, and biases. So this is, we want to plug in it into this equation so that we can actually see exactly how this works out in practice. So if you plug in the bias, of course, the bias also has to be quantized. Usually in a neural network, the bias is added after the operation. So let's look at the final one here. So we usually get the output given the scaling. So we will actually bundle this to be one value at the end of the quantization. We have this as a scale. We have the quantized of the weights, the quantized weights and the quantized inputs. And then you add the quantized bias, and then you add the scalar or the Z point of the output. So this is how it works in practice. So this is like a summary for this. So the same happens for convolutional layer. So this is just a math. You convolve basically the quantized values, you add the quantized bias, and then you scale this using the scaling point, which comes from the scaling point of the weights and the inputs divided by the scaling point of the output. And then you add the Z point of the output. So this in a quantized setup, this is actually how the operations work. For example, you use the PyTorch libraries. This is like how they do the quantization. So you have quantized inputs, and then you have quantized weights. You do the operations that you wanted, maybe the convolution or matrix multiplication. And then if they were, for example, 8 bits integers, we usually then, if you multiply an 8-bit by another 8-bit, that number can be larger than what you could represent in 8 bits. So we increase the bits to 32 in integers, and then we add the bias, and then we divide by the scale. And then if we divide it, then we can now go back to 8 integers, 8 bits, and then you add the Z points, and then you have your quantized output. So basically now this is like the step-by-step process of quantization in a hardware implementation. So in summary, this is like a uniform quantization. So it's basically a uniform, it's to map a real value X to a quantized B-bit integer via an affine transformation defined by the scaling factor S and the 0.Z. And this is the formulation. So we basically have a clipping range, which represents the dynamic range, and then 2B being the bits we are using. So we can find the scale, and then the Z point was derived as this, and therefore we can have this. So you notice if we change the number of bits, we have a difference in the step size. So the more the bits you have, the higher the resolution of this transformation. So then this lets us to move into the next part of still on how to quantize. So we have just talked about on quantizing a tensor, but in a neural network, we have several layers and several tensors. Then how do we quantize? So we could do it per tensor. Basically, you can do it by every filter. You can do it per channel. We can do it using, we do it per group. But again, this depends on the characteristics of a layer of the model. So some layers have a high dynamic range, some layers have a low dynamic range. Then you cannot quantize all of them uniformly in terms of like using the same scaling factor for all the layers. So you choose based on the distribution of data for each of these layers. So because of that, then we have other techniques of quantization where we use codebook quantization. So this is especially useful when the distribution of values is not normally distributed. So where we have for example, in a weight layer, we have this kind of distribution there where we have some values distributed differently from various ranges. So in this case, we can use a code book in like more of a lookup table to describe these weights. Of course, this had some like it needs a hardware support because you're basically building like more of a lookup table. An example of this is the k-means based weight quantization. So what we do here, so if we have this tensor, we bundle up based on k. So we can say every like two closely related weights, we select one, or we find one that can represent these two. So in this case, we are using 2 bits. And for 2 bits, then we realize that you can see some of the weights have been clustered together, the blues based on this color. So from these blue values, we can use the number 2 to represent them. And then we form these centroids into a code book. So we store this in hardware and then match their indices to the various values of the weight. So what happens here is that in this case, we are able to compress this model. So we are only storing the centroids and the indices. And remember, the indices are just basically two bits in this case. So we are saving on the size of the memory, but of course, we are still doing the operations in 32 bits because we will have to scale them back to the original. So this codebook quantization only saves us in terms of memory, but the other techniques save us both on memory and computation, as we will see. So then how do we know how many bits we use for this quantization? So this is an experiment that I will link the paper later. I tried to find, so as you can see that if the more bits you use, the higher accuracy you retain. So you can, if you start with 1 bit, actually you lose entirely. You break the model. So if you give it more bits to represent it, you have better accuracy. And so the challenge is to find the sweet spot. And for example, in this convolution layer, they found that 4 bits were actually retaining some level of accuracy. So it depends on applications. Some applications are okay with 50% accuracy. Some models are really critical that you do not want 50% accuracy. It's just based on applications. So for this, for example, you see you are gaining nothing by increasing bits. So in this case, then you will rather stick with 2 bits than 4 bits because there's no difference. So there's another proposed method which they try to find how many bits to use in representing values. And in the case of distribution of weights, so you can see there is a range where there are very few weights, and there's a range where there are more weights. So this Huffman coding technique then proposed that in these infrequent weights, then we can assume that they are very important. So we use more bits to represent these fewer weights. And then for those that are many, then we can use less bits, assuming that they are less important. So this is the essence of this Huffman coding, so as to find how many bits we use for quantization. So combine this is a paper that combined these three methods, that of pruning, which we will discuss in the next section, quantization, and this Huffman coding to find the number of bits to represent the weights. So they show that they could actually reduce, for example, VGG16 is one of the largest CNN in terms of size, memory size. They could reduce it by 49 and without losing any accuracy. So this is how powerful these methods can be when combined, and they can reduce really the memory consumption as well as the computation workload. So that was about uniform quantization, which works well when we have, which normally works well in most cases. But it is also noticed that most weights in a neural networks follow this distribution. It's a normal bell-shaped distribution. So we have more weights closer to zero than the extremes. So then if we use a uniform quantization, meaning we are giving same importance through the distribution. So then they proposed using non-uniform quantization that gives more focus to most of the weights that are in the model. So we focus to those that are more than those that are less. This is kind of the opposite of Huffman coding. So, however, the problem with uniform quantization is that we have to have a special way of representing this in hardware. So that is the only trade-off in this case. So one method in non-uniform quantization is what we call the logarithmic quantization, which can really encode a large dynamic range of data. Because a log, when you have the log scale, actually, when you do plotting, you're able to really encode data in a very large dynamic range, even with fewer bits. And so the other advantage of this representation is that because we're using powers of 2, this is a very natural encoding of data in hardware. So rather than having multiplication, you can implement operations using shifting of bits rather than doing a normal multiplication, which is really intensive in terms of power. So for example, if you have this, if you have represented your weights in this format, say 2 raised to 3, and then this is your input, 1, 0, 1 in terms of binary. So rather than having these values, this is usually 8 and this is 6. So if you did a multiplication using a normal, it will be very expensive. But if you did using this logarithmic, you are only shifting this number to the left 3 times. So you are only adding zeros to the right. So this is really very fast in hardware. So this is the advantage of maybe this technique. So there are also other proposed techniques around non-uniform quantization. One of them is powers of 2 quantization. Basically, you having these values represented using powers of 2. So you limit your scaling factor to powers of 2. So you have a value multiplied by any power of 2. So this is one technique. And then the problem with this, of course, is that this region here, there's a rigid resolution region where you have more resolution closer to 0 than those are far from 0. So another technique was proposed, which was called additive powers of 2. So we encode the values such that the powers of 2 are a sum of other powers of 2. So then we are able to distribute this resolution a little bit further to encode this more precisely. So this is really a nice technique that was proposed. And I actually did this as my master's. I applied this in my master's quantization project, and it was really it was able to reduce the model size to kilobytes. So you saw some of the models are in megabytes. You can actually reduce this to kilobytes if you use 2, 3, 4 bits. So the other concept in quantization is then when do we quantize? Usually in these deep learning models, so we could do it after training. So you have a model that is trained, and then after the training, you quantize the model. Also, you could also do while you are training, which is called quantization aware training. So these two methods have different impacts to your process. Usually, it's very easy to do after quantization, but as we said, quantization introduces losses, so you are losing a lot. So sometimes you may lose a lot of accuracy in this post-training quantization. So while quantization aware training is actually trying to recap or trying to regain what is losing in a process we call QAT. So in post-training quantization, as we said, there are two values. Of course, we are trying to find the scaling factor and the Z point, as I earlier said. Normally, weights and biases are static after training. So you have them fixed, right? But the activations are usually changing for every set of input. So if you did a static quantization of these weights and biases, then how do you determine the scaling factor or the Z point of the activations? Then this is really, if you just choose a random value for this one, you will aggressively lose accuracy. And for this reason, they have what we call calibration. So you use a set of inputs, get some statistics, running statistics using this calibration data to find the scaling and the Z point of the activations. Activations are those intermediary values you get from the convolutional layers. So this is the typical post-training quantization, is that using this calibration data, it's a small set of images, for example, in an image classification example. Then you use those calibration data to determine the step size for the activations, and as well, of course, we know that the step size of the weights can be determined without any data because it was static. And then you basically check if your model is preserving some satisfactory accuracy. If not, then you can do what we call fine tuning, is try to play with the parameters of the scale and mostly the scale. So the note here is that doing this naively will result in significant loss of accuracy. Then that's why we have a more robust technique, which we call quantization aware training. So in this case, we are trying to improve the performance of the quantized model because quantization introduces losses. So the thing we do is that we train the model while taking the quantization into consideration. So this will minimize the loss of accuracy and sometimes can even improve the performance of the quantized model. So this is a representation of the flow of data in a model. So there's a forward path and the backward path. So you have inputs, you have this layer operations. This could be the convolution layer, a fully connected layer, which have weights and and then you get your outputs. So that is the forward path. The backward path is usually useful when you are training, because in training you are trying to update the weights so as to optimize your output accuracy. So then how do we improve performance of quantized model? So in quantization-aware training. So of course, we have to introduce this activation because we have to factor it during training. And of course, we understand that how we find the activation. Okay, how do we train a model? That we're using a gradient descent algorithm, which is trying to find the derivative of these weights and activations. But we know that the derivative of any discrete set of numbers is 0. So for that reason, we have what we call fake or simulated quantization. So where we simply, when we are doing the quantization-aware training, we represent all the values in floating point rather than having them in discrete point. But they are actually learning the effect of quantization. So in this case, fake quantization means you quantize using the chosen parameters and then dequantize them back to the floating point. So you are taking factor of the quantization process. So here is how it goes. For example, we have an input matrix. You quantize it to this quantized weight matrix with these parameters, and then we have the quantized weight. Of course, it's after quantizing, right? So because it's still in floating point. So this is like the process. So we have a fully pre-trained model. Mostly we start with already a trained model, but again, you can also do this from scratch. So we are using these gradients to find the loss of precision. So this is just a process. You have the input, you quantize it, and then do the operation using the weights, and then you get the activations, they are quantized, and then you do it in the reverse direction. Of course, we plug in the equation that we derived earlier. But to find the gradients, as I said, in discrete values, the gradient is always 0. So if you, this is how the backward process works. If you have this gradient being 0, then we are not going to learn anything in the backward process. So then there was a method that was proposed to actually assume this is 0, this is 1, we set this to 1. So like we're able to learn the backward gradients. So it's like you make it transparent in a way. You just, okay, this is the process. So because of this being 0, we just replace this with 1 so that we can learn the impact of quantization. And so we are able to then update the weights during quantization. So I think even in, I will show this, in the practical session, we will have some code that tries to do this. So generally, this is how it moves. So we are using this fake quantization and like using the straight through estimator that sets the derivative to 1. So during the learning, the forward process, we update these values. And in the backward process, we use this gradient that is we derive the derivative of the loss in respect to the outputs, so that we try to minimize this loss in the process. So how then do these two techniques compare? So post-training quantization and conditional-aware training, both symmetric and asymmetric. And in this case, we are using either per tensor or per channel. This is the granularity. So you can see, for example, in these models, with post-training, we actually lose them. With asymmetric, we lose the model completely. So it's like it broke because now we have 0.1% accuracy. And for symmetric, so symmetric is like better. And in this case, they did per channel, not per tensor. They got at least some better accuracy. But now when you use quantization aware training, then you're able to recover actually the model, the original model's performance. And sometimes it can be better than the floating point because you are trying to recover it, and then sometimes you can train it to be more close, better than the original one. So this is the impact of these two quantization techniques. So then is it possible to like even use less bits to represent the weights? Yes, it's possible. So usually 8-bit quantization is sufficient for many applications, but we can still push it to even using a single bit or even two to represent the values of the weights. So there are two techniques here. I will just mention them briefly. One of them is the binary neural network quantization and also the ternary quantization. So in binary, we are using a single bit to represent a value. So this can be either positive one or negative one. So we're using single bit. But because 0 is very important, which can actually help us improve the network also, they introduced 0 in this so that we can represent this using 1.5 bits, but this is in hardware, it's actually 2 bits. So how binarization works is that we, if a value is either greater than 0, we use a positive 1, less than 0, we use negative 1. And this, you can also have other ways of determining this using this another stochastic binarization technique that uses another technique of the sigmoid function to determine whether we have 1 or negative. But now the most important thing about this is that in this case, the operations are now very much simplified in that we are now going to use a single gate, in this case, an exclusive NOR for operations, and by simply counting the number of ones. In modern hardware, it can be very fast. And so we will simplify it will be very fast and very energy efficient. But again, of course, with this binary quantization, we are also going to lose accuracy in significantly, as I will show. For example, these are some of the binary quantization techniques. These are published works where we quantize only the weights to 1 bit. And here they preserve the activation to 32. So they lose accuracy by this. And now if you quantize both the weights and activation to 1 bit, you see how much you lose. You really lose more because you're only representing this into just 1 bit. But of course, the benefit here is that we are gaining really a lot in terms of memory. So you are reducing the memory by 32 times and the computation by even approximately 258 times, meaning this would be extremely fast. But again, we have this trade-off of losing some accuracy. Again, this is also application-based. Sometimes this will be okay. So the other technique is ternary quantization, which now uses 3 levels of quantization, either -1, +1, +0, and it also gives us the advantage of effectively pruning because we have a 0 in this representation. So if your value, some of the values are 0, then there will be no computation in this case. Yeah, so this is just, okay, this is to show how ternary also works in comparison to the binary. We have like better performance with the ternary because now we have another level of representation. So there are other techniques, advanced techniques, but I didn't spend much time to make it here. But we can have mixed precision quantization. Here, in this case, we can have different layers having different bit widths to represent the values. So we can have one layer having 4 bits, second layer having 7 bits, and so on. Of course, this also comes with the trade-off, like in hardware, then you have to consider this, how to implement this in real hardware. But it's something that is possible if you're able to, maybe what some layers are very less sensitive, some layers are very sensitive. So you can balance that and then find a more optimized way. Yeah, so this is basically the whole concept of quantization. Maybe if there are any questions, we will discuss about. Yeah.
One question that comes to mind is that sometimes if you were to apply a lot of quantization and find, oh, now the precision isn't quite good here at this particular connection, could you perhaps improve that by saying, making that particular edge in your neural network thicker? So you have one quanta representing the high significance part of it and another representing a low significance part of it. Or is that messing up the architecture too much?
Okay, yeah, so I think really this is like a game of balancing. You could notice that, as I said, there's these distributions. So as we said, some mostly give the distribution of weights in a layer. But you may notice that one layer has a very different representation. As we also said here, like it could have this distribution of weights. And in this case, you notice that maybe representing this layer in Huffman coding would be more appropriate for this particular layer. And then in the rest of the layers, we have this uniform distribution. So how to choose is basically like, it's also like part of what we will talk about in neural architecture search. Then you can now put this into a search space and then see how to find the best for you. But again, the trade-off is that for every method you use, there's also a trade-off. For example, if we use a non-uniform quantization, for example, here we have more values close to 0. As we said, this non-uniform quantization is not like supported in most hardware. Then it means you will have to change the hardware you use in this case. But it's really a trade-off, but it's quite a trade-off. But there are cases where you just have to find the balance. Yeah. I don't know if that answers.
No, maybe not the same thing. Oh.
Well, maybe you can come up again. So I.
I have a question. In one of the slides, they were written like it was in post-tree quantization, right?
Yeah.
It was saying that if it does not perform well, the post-tree quantization, then we have to like train it again.
Yeah.
So when we say like we have to train it again, what does it mean? Like we have to do training away quantization away training, or like we have to do some other training in that tool? Like if post-training quantization is not working correctly, so we have to do the training quantization away training in that case.
Yeah, so normally post-training quantization works very okay, relatively okay with even up to 8 weeks. Now, when you go beyond 8 weeks, you significantly lose accuracy. So to counter this, that's when you now post quantization working. So where you can begin with a trained model that you had before, and then you train with quantization being part of the process. So as I said here, you are in the forward part, you do the fake quantization. You quantize and then you quantize back 32 bits and then get the accuracy, right? And then the backward process, you use the gradients that we mentioned about, and then you update the weights, right? And then you do another round. You do that as you monitor the accuracy of the model. And then usually by doing so, you are improving the model's accuracy because you are updating the weights in this case. So it's like an iterative process of trying to recover from the effect of quantization.
Do we have any more questions? So we can take a 15-minute break.
Yeah.
Get some coffee, and then we can come back at around like 10:40 after 15 minutes, and we can resume pruning, right?
Yeah. So the next is for pruning, which is like an additive to this method.
Yeah, and we'll also be seeing some demos, quantization and pruning. So thank you.